Hello, this is Dave at Polycom Studios, where we have for you what's new and hot in the world of audio. Have you ever wondered what sound really is? I mean, you turn your stereo, your TV, your conference phone on, and the sound just comes out, right? Well, what if you want to know a little bit more what's happening behind the scenes? Well, we've got a treat for you today. This guy here knows that stuff down. So, he has 21 years of information technology background and 10 years as a technical trainer, and even more, he has made and delivers the Vortex technical training for Polycom. Please welcome Lance Wakeman.
Hi, thanks.
How you doing, Lance?
Good, thanks. How are you?
So, when we talk about audio, what does audio mean?
Audio is just sound in a medium, sound waves in a medium.
Medium, like psychic medium?
No, actually, it's the physical environment that the audio is being transferred through.
Okay.
That medium could be air, it could be water. Sonar is using water as a medium. The movie Alien has a tagline, and it says, "In space, no one can hear you scream." And I always kind of liked that because it was always kind of weird to me. But you think about it, space is a vacuum. There is no medium for the sound to propagate through. So in space, no one can hear you scream.
But sound can also be propagated through a wire by an electrical signal.
Gotcha. A signal, so that kind of just goes through the wire, through the air. Like, what does it do when it hits your ear? I mean,
Well, in depending on the medium, determines how it's going to affect the listener. In the air, sound waves bombard our ears, and our ears vibrate to pick up that sound. And so the air is the medium that is transferring those waves.
so the air kind of pushes on your ear. It
Exactly. When the air changes with sound, it creates these pressure waves. And as the air's pressure hits your eardrum, the eardrum will then vibrate. And that vibration is then sends an electrical chemical reaction to the brain, and then that's how you experience or sense audio. And that's the air pressure changes on your eardrum.
So it's like a drum. So something's like pressing on a drum.
Right. The air wave, the waves that the audio has created in the air, that compression of the air, that vibration that is created is actually pushing on our ear.
Oh, cool. Okay, so you have this pressure pushing on your ear, and then what? And it creates electrochemical, and so now I know when something makes a sound, it comes in and it pushes on my ear.
Exactly.
Tell me more about how it pushes on my ears thing kind of thing. Does it have measurements? Does it have...
Yes, just like anything, it's measured, right? So what we have is we actually have what's called the sound pressure level.
Okay.
That's what we kind of use as to differentiate how intense the sound is, or how loud the sound is. It's based on sound pressure. It's usually measured in dynes or pascals, and those are. That's the level of loudness that you would hear. But usually we measure it in sound pressure level, which is measured in dB. And the sound pressure level is actually that sound pressure in relation to some other base pressure, usually zero.
Gotcha. I kind of heard about sound pressure. Maybe is that like SPL or something?
That's SPL, exactly. It's dB, and it's measured in dBs. So sometimes you'll see it dB SPL, or you'll see SPL as a small little script for that, for dB. But it's basically measured in dB or decibels.
Because I know when I get new audio speakers from my trunk, it's going to say, RMS, or it's going to say WTS, or it's going to say, and SPL, I know the bigger ones are better, but when I turn up the volume on my car stereo, I don't see dynes or pascals. I just know if it's too loud because, mom or girlfriend gets mad, or, so how do I know dB or SPL? Because I know if it's too loud, it's bad for me, but how does that work? How are those related?
Well, for example, in a quiet room or just like a living room, there is what's called it's about 40 dB. This chart right here can show you where an average living room is about 40 dB of sound pressure level. And that sound pressure level is about, average for a quiet room. And so if you go into a living room, you'll experience about 40 dB and maybe louder depending on if you have some sort of equipment in there that might have make noise like a fan or something like that. It might increase the background noise.
So the noise we're making right here is maybe about 40 dB.
Well, actually, the noise that you and I are making is about 60 dB of audio, sound pressure level.
Oh.
The 40 is the background bass, is the bass, and so what conversational speech, as the chart says, is that we're about 60. Now, I usually go probably more like 70, but they say the average conversational speech is about 60. So as you can see here, that the 60 and the 40, they're 20 dB above each other, but you would think that's only 20 or so units above. But in the Pascals, that's actually 10 times louder than if you were to measure it with the dB SPL meter. Yeah, it's 10 times greater.
So I've got to be louder by a certain amount to be for you able to hear me. So if everything was maybe 60 dB, like everybody's being really loud, in order for you to hear me, we'd have to be at
80 dB.
80.
According to Don and Carolyn Davis from Designing for Intelligibility, a rule of thumb is that you should be about 20 dB above background.
So that's why in a quiet room you can talk softer, but if you go into a disco or whatever, you have to really yell in order to be overheard, because a disco is about 100, 110, and so in order to be heard, you got to be above that. And I don't know if you think about it when you go to a disco. If you need to talk to somebody, and it's not like the movies where the music's going on and they're just having a conversation kind of like you and I. That's not how it works. In the discos, they've got it up to 100, 110, 120. You actually have to get close to somebody's ear to really talk, and so that distance helps create the ability to be heard.
But when someone gets up to that close to me and I'm in a dance place and it's really, really loud, and then they start yelling at me, it hurts. I mean, is there a number where I better not go because I'm gonna?
Well, if you notice here on the chart, the threshold of pain is about 130. I think it's actually lower than that, because if you've ever been on a street side and had a fire truck come by, that actually hurts your ear, and the chart says it's about 120 for sirens. So if that's the case, then I would say the pain threshold is about 120. And if you've been into a disco, they're about 100 to 110. So they get quite loud, and you're only about 10 decibels away from where the threshold of pain is actually getting ready to start.
Gotcha.
If they're at 100, 110 already, in order for them to talk, they're gonna have to get up to the 120, 125, 30 area, and now you're into the threshold of pain.
Cool. Okay, so we're getting a little sense of how audio works, and there's pressure on your ears. I'm starting to get that. And then there's the decibels is also how it's also measured. There's a relationship there, you said.
That's right.
And you said you can kind of show it to us on this chart.
That's correct. This column right here shows you that it's in pascals, and we talked about pascals. It's just a form of measurement. But if you notice, at the average living room is 40 dB, and it's actually labeled as 0.002 on the sound pressure, the pascals. You go to conversational speech, it's 20 dB above, but it's actually 10 times louder in pascals.
Whoa.
Yeah, it's actually 10 times greater. The sound pressure level is actually a logarithmic scale.
So logarithmic, I usually, if something gets larger, but like a volume control, it actually gets larger faster. Is that
Exactly. It ramps up much quicker.
Okay, and that's because some audio engineer thought it was cool, or is that kind of why did they do it that way?
Well, back in the 20s, some scientists at Bell Labs created the transmission unit. They didn't really know what else to call it, but then they decided to change it in respect for Alexander Graham Bell, who started the labs. They called it the Bell, and so they took that transmission unit and called it the Bell. because Alexander Graham Bell was the founder of Bell Labs, and then they basically took it and just dropped the last L, became BEL, and so they named it after the founder, and they were paying homage to him because he is probably the most influential person. We don't think about it in today's day and age when we're talking about speakers and microphones and all this other stuff and transmitting audio. We don't think about it, but he was really the first one to transmit audio from two dissimilar environments. He actually put that on a wire and sent it, and that's what we know today as a telephone.
Watson, come here.
Exactly. I need you.
Cool. I remember that.
Exactly. Yeah. So he actually was the instigator to just about everything we know today, because he took a microphone, he took a speaker, and he combined them together with radio or a signal, and not radio waves, but an electrical signal, and was able to transmit that over a wire.
Cool.
Yeah.
So we still use his name, Bell. But I guess it's too big. That's why, or it's too small because deci means bigger, right?
Well, actually, deci means smaller.
Oh,
it's 1/10 of a bell, because they found that the bell was too high, or the transmission unit was too high, and they had to take it down to 1/10 of what it normally would be at, or what they figured it should be at. And so that's where we get the decibel from. So it's 1/10 of a bell, and that's where we deal at in the sound pressure level, is in decibels. So that's where the decibel comes from, or dB for short.
Gotcha. Okay, cool. So we got a little sense of sound pressure levels when we're talking about audio, and we're talking about how we measure that with decibels. But okay, that's a little bit esoteric. What happens if I have my friends in my garage and I want to record a band? How does sound work there? I mean, I just grab a microphone from Radio Shack, stick it next to them, I'm good to go, right? Or
You need to do more than that. Just pointing a microphone at them doesn't really do everything you need to do. Eventually you're going to need to take that signal and do something with it. You're going to need to manipulate it. But you're going to need something in order to capture the sound, and that is a transducer, or commonly known as a microphone or speaker. So that transducer works a lot like your eardrum. It has a diaphragm on it that when sound hits it, it will vibrate, and by creating that vibration, it then creates a signal, an electrical signal, that then can be captured and manipulated.
kind of like you said, the ear. The air pushes on the drum, and the drum does something electrical, and so it's like a mini ear on a
Exactly.
on a string.
Exactly.
Oh, cool.
Mm-hmm.
So I'm gonna stick the microphone in front of them, and I have a speaker on the other end to know that the microphone's picking up the sound. I mean, there's got to be more to it than that, or else I can just, I don't need to buy records from.
Right. No, there is definitely a lot more to it than that, because you have to manipulate the signal. When I'm talking about manipulation, I'm talking about the signal when it comes out of the microphone is too low to really do anything with. So first type of manipulation we have to do is we have to send it through a preamp, and that preamp then takes it up to a what's known as line level, so that now we can do something with it.
I've heard these things, preamps. I mean, I got my amp and I plug my stereo into the amp, and then the speakers come out. I mean, why don't I just use that amp and I plug the microphone into that? I mean,
No, it's because the signal is so small coming out of the microphone. If we just had a regular standard amplifier, it wouldn't be able to do anything with it because the level is too low. So we need a intermediate amplification that we can then take and get it to a level where we can do something with it.
well,
That's right.
okay, so I've seen those big audio rooms where they show pictures in the old days, and they have tubes and all this stuff, and people say it's analog, and now you have computers, and that's not analog, right? That's
It's digital.
okay. So what's the difference? I mean, if I plug, I'm sure there's pros and cons or whatever, but can you break it down? What the heck's the difference?
Well, analog is a continuous waveform. It's a continuous signal, and that's what's coming. That's what I always say that we live in a analog world, but we deal in a digital environment like the computer, and we have to convert that somehow. We have to take that analog wave and we convert it to ones and zeros or bits for the computer.
Ones and zeros.
Ones and zeros, digital. In digital, if it's high, it's a 1.
high.
If
to
it's
1.
low, it's 0.
And there's nothing in between. It's
No,
just high or 0.
It's either on or off.
Like a light switch.
Exactly. It's either on and off, except for a dimmer. A dimmer is analog.
Dimmer is analog. It's not
whereas
going
a
to be
light,
digital.
right? A light switch is digital.
Gotcha. Okay, so now I have analog, and people in the old days say that I want to use tape, I don't want to use digital, and they say better audio, and you have audio files that say analog is better, digital is better. Can you give me a couple of pros and cons why one would be better than the other?
Well, it really depends on what you're trying to do. There's a lot of times the question is, well, which is better? Should I do this or should I? And the answer is usually it depends. So it almost always depends
I hate
on
that answer.
Yeah, because it's not very very informative, is it? But you can take that and build on it. So what are we going to do with it? What do you want to do with it? Do we want to, for example, we want to do video conferencing with it? Do we want to send it to a far end video endpoint? Well, we're going to need to convert it to digital. But we don't necessarily want to amplify it in the digital realm or the digital domain. We want to amplify it in the analog domain first. Because when you have an analog waveform that is going through, you have literally infinite number of points per cycle
Right.
that you can get that you amplify. So you get a much better amplification that way. And when I say per cycle, one waveform per second is a cycle. So
Okay.
Also called a hertz.
I've heard of that.
The German guy named Hertz, not the car rental agency, but the German guy named Hertz found that a signal propagated over 1 second was a cycle per second. And that's where Hertz comes from.
Okay.
And so that cycle then it gives us a lot of flexibility on our amplification. The problem is that if we amplify it too much, then we start getting noise. When you have an analog signal, you have this waveform that has infinite number of points along it. So when we amplify that, we're amplifying the whole signal. Well, when we amplify the whole signal, we also amplify the noise that's on that line as well, on that signal, because every signal has noise to it. That noise will then grow with the signal, okay? So when we get to a certain point, we can't amplify it any more because we have gone beyond the signal, the noise floor for that signal, and then the audio of interest is no longer any good to us. So at that point, then we can convert it to digital if we wanted to.
I've heard of something similar. It's a signal, and it's connected to noise, signal, noise.
It's really the signal to noise ratio.
Okay.
That's where the signal is large enough above the noise that you can basically discern. And we use that a lot in the conferencing world and in sound reinforcement.
So we want to try and maintain that rule of thumb of 20 dB above background in order to maintain intelligibility.
For example, when we were talking about the average living room being a 40, conversational speech is 60, that's exactly what you want to be. You want to be 20 dB above the ambient noise of that room. If that ambient noise is higher, then you're going to have to be higher, just like in the disco.
So a good minimum thinking for conversations is 20 dB, but do you want better than that, or is that pretty good for recording audio?
Well, for Vortex, we always want to make sure that we're 20 dBs above audio because it's all conversation to us.
Got it.
Okay, so from a like a music standpoint, I'm not sure how that would actually play out, but from a video conferencing or teleconferencing environment, it's all conversation. It's all voice that we're transmitting. So we want to be 20 dB, and sometimes that's not easy to do.
Wow. Really? So, I mean, I know in my garage, I put egg cartons on the walls and some carpet and a cinder block and stuff like that. And that kind of, I can't hear this stuff outside, and Dad likes that, but it gets kind of the sound.
It's called a dead room.
Ah.
Because what you're doing is you're taking out the reverberation. You're taking out the reflection of sound coming off the walls and the windows and the floor and the ceiling and all this mixing in, because that adds to the noise floor. And that noise will build. If you've ever been in a concrete stairwell, you'll know that when you talk, it's very live. You can really hear the sound bouncing around. If it's just you and I and we're talking, we don't have to talk that loud because the reverberation isn't that great. But if it's lunchtime and everybody's leaving for lunchtime, there's a lot of people in there,
Right.
and it gets really noisy really fast.
Right.
And so then you have to talk louder, which creates more reverberation.
Right.
And so they have to talk louder, which creates more reverberation. And then you wind up having this whole increase across the spectrum where everybody has to talk louder, and because the noise level keeps raising, the noise floor keeps raising. And you have to be 20 dB above that.
When you talk about reverb, I mean, I've heard of that, and on my guitar amp, I can turn up
Yes,
reverb, and that
right.
kind of sounds like a little bitty of an echo. But you're saying reverberation is way worse than that. It's not a cool effect.
Well, sometimes it's kind of a cool effect. Like when you're in an open room and you say hello, and you kind of hear hello back at you. It's kind of fun to play with that and stuff like that. But when you're actually conferencing, you do not want that. You don't want that noise at all. Because what happens is that when we send that to the far end, then they'll pick that up and they won't be able to discern the speech from the noise. So it's very bad in conferencing environments. And humans like a little reverberation.
Okay.
We're used to it bouncing off the walls and the floor and everything like that. So we're used to a little bit of it. But if, for example, in the concrete stairwell, it gets to a point where we can't deal with it. Basically we'd stop talking if that was the case. If it got too loud, if there was too many people in there, too many people talking, and
Right.
all this reverberation. So we like a little bit of it, but when it gets too heavy, it just basically drowns us out, and we can't concentrate. It's actually we lose concentration because of it, because there's all this extra noise hitting our ears.
So you said when we put up all that carpet and stuff in my building, it made the room dead. So I took away too much reverberation?
Well, it depends. And once again, it depends on what you're trying to do. In a recording studio, for example, in New York, they build a room within a room. And they have a tendency they have to do that because they have like this, I forget the exact frequency, but it's like they have this 20 hertz rumble or 40 hertz rumble that they can't get rid of. And so they have to build this room, and then they line it with all this absorption material
Okay.
to get rid of the reverberation. And you ever wonder why they wear headphones when they record?
Yeah, I figured. I mean, you're playing music. Why aren't you listening?
Yeah, why aren't you just listening to the music?
Yeah,
right?
right.
The reason they wear headphones is because those rooms are so dead, it's unnatural to the human. So they get feedback through the sound system to give the entertainers some feedback where they don't get that feedback. They don't get the reverberation off the walls because they're dead rooms. And a live room is something that's really reverberant, like the concrete stairwell, that gives us too much reverberation.
So I almost want to have, when I'm playing for an audience, a lot of reverberation, but when I'm recording, I don't want it because it's going to make it more tough to hear. It's going to be...
Exactly.
Okay.
Yeah, exactly.
So you're talking about there's reverberation, and you're talking about, the dead room is doing it too much. What is the best way? Is there some technique to get the room? You talked about there's sometimes a room within a room, but if I'm setting up a conference front, I can't do a room within a room.
That's right.
What's a better way of doing it?
Yeah, it's not financially feasible to do that every time you want to build a conference room. But there are things you can do. Carpet on the floor, excuse me. You have the carpet really helps because most buildings, most conference rooms, and most commercial buildings are made out of concrete and steel. These are the worst when it comes to reverberation. There's about a 2% absorptive rate when we're talking the absorptive properties of concrete. It only absorbs about 2% of the audio. So when you take that 2%, it doesn't do you much good. So you put carpet on the floors, you put acoustic tiles in the ceiling, you put sheetrock, which helps a little bit, but it doesn't help a whole lot. The best way to do it is if you need to deaden the walls, you need to do a parallel. You only need to do one wall at a parallel. So that one wall, you might put these acoustic panels on. They're panels with insulation that have fabric around them, and they look fairly nice. And you can use that to deaden the sound. But if that's not feasible, then you can use drapery. Just put drapes across, heavy, thick drapes, and then that'll help absorb the wall. And it doesn't look too bad. You can make it look nice in that respect. I always tell my classes the worst thing you can do is put a conference room with a big window. If you have a window, put drapes in front of them. That darkens the room, but you will not have the sound coming in as well as sound being reflected back. There's a company that has their conference room right next to where their big heavy trucks come through.
Oh, no.
Because that's their bread and butter. They have big dump trucks, and that's what they sell, and that's what they do. Well, the worst thing you can do is have a conference in there and have these trucks going by, creating all this noise and rumble and everything else. So they found out that wasn't the best place to put a conference room. Conferencing is best done inside a building where it's surrounded by basically building material. You don't want to be to the outside. If you're having just a local meeting, that's one thing. But if you're trying to teleconference or video conference, then you definitely want to be in a room that's an interior to the building.
So we were talking about how you said sometimes you want to amplify in the analog realm because you have a lot of there's more samples there's more stuff to that.
Right. There's an infinite number of points on that waveform that you can amplify. But at a certain point, it becomes not feasible to amplify it anymore. And at that point, you can convert it to digital, and you can still amplify it in the digital domain. But now you're limited by the number of sample points that you have on that wave that you took from that wave. So it's not going to be 100%, and you're limited.
If you have a 48 kilobit sampling rate, you will only get 48 kilopoints per second.
So you're only going to see that many. And I said there was infinite with the analog, so now you've basically finite. You have a finite number of points that you can deal with.
So you're talking about how there's a certain kind of sampling rate from analog to digital, but how do you get from analog to digital?
Well, you need an analog to digital converter.
Is that something kind of like when you get little boxes to plug in your computer, and I can plug a microphone into the box and then it records into a hard drive? Is that something like with?
Yeah, it's very similar. It has an A to D converter in it, and it's probably doing some amplification and other things too. But generally speaking, yeah, that's what it's doing. It's converting it to digital for you.
So, okay, so we've been talking about you got your sound, the sound hits the ears, you got microphones and it acts like an ear, you have the sound that goes through and you want to amplify it or manipulate it, you said.
Manipulate.
So what kind of manipulations? Like you said reverberation, but we don't want to try to fix that electronically, you fix that with the walls.
That's correct. We could do that, but it would be so cost prohibitive, we wouldn't be able to remove the reverberation. Nobody would buy the box. So it's easier and better to do it by putting absorptive materials on the walls.
And any other kind of manipulation? What if you want to make a guy sound like a girl?
Well, yes, you can do that too, but we don't actually do that in the conferencing world. What we do though is that we might do noise cancellation.
Oh.
So we would take that signal and we would remove the signal. We would remove the unwanted information. So we can also do acoustic echo cancellation. Acoustic echo cancellation is where we have echo on our system, on our video conferencing system. So if I'm talking to somebody on the far end, their voice comes through my system, gets sent through my speaker, is picked up by my microphone, and then sent back to them. That's called echo. And we can take a representative sample or a model of the speech that's coming to us, and we actually do the echo canceling for the far end. So when the far end's talking, it goes through our signal processing vortex. We take that digital, we sample from it, and then send it back out minus their own speech, and allows them not to hear themselves come through because it's very distracting and it doesn't add to the intelligibility of the circuit.
That's really cool because I've been on conference phones and it feels like hello, 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 hello. And you can
actually hear it.
When you actually do that kind of noise cancellation or echo cancellation manipulation, does that affect the quality of that? Am I going to sound a little bit like this now, or is it going to do
Absolutely not. If you have a good signal processing device like a Vortex, you will then, you shouldn't hear any difference. If anything, it'll be much clearer and much more intelligible. And that's what the Vortex is all about, is making it more intelligible. Cool. Polycom spent a lot of time and a lot of energy creating 14 kilohertz audio and things like that, which As you know, the phone system is only 4 kilohertz at best, right? So we're up to 14 kilohertz now, which gives us the ability to be able to understand each other much easier and makes our meetings and our conversations much more productive.
But I can get that through a phone line to the other guy.
Yes, you can.
So is that because you went from analog to digital, and then is that how that works? You can get more signal through the digital? Or?
It depends. It depends.
There that is.
There it is again. If you're using an analog phone, chances are no. A regular set-top phone doesn't convert it. It usually just sends it out in analog. If you're using like the Polycom VTX 1000, it actually converts it and then sends it out. And as long as you're talking to another VTX 1000, then you can hear it. But other than that, no.
So you're able to get 14 kilohertz out of that 4 kilohertz line.
That's
That
correct.
is cool.
That's really cool.
And I don't have to buy a digital subscriber line or anything else. I can do it with a normal phone line.
That's correct.
That's very cool.
Now, if you're talking about video conferencing, then you would have an ISDN line where you would have multiple lines, and that's digital. And so we convert just about all of our video signal and audio signal for a video conference into digital and send it out to the other end.
When you set up similar a Vortex for just maybe conference or for video conference, do you have the same problems with that? You said the room. You have to make sure the room's good. You have to.
Oh, absolutely. When you're talking either teleconferencing or video conferencing, and you're talking to somebody on the other end, if you have reverberation or background noise or things like that, and you don't have noise cancellation, then it'll go to the other end and you will hear that, and you won't be able to discern the noise from the sound of interest. And so that's why a lot of sound reduction or noise reduction, and reverberation reduction and acoustic echo cancellation and even filtering is done to make the signal much more intelligible to the individual on the other end.
Very cool. Very cool. Well, if I can wrap up, we heard a little bit about how audio works, whereas the sound it gets in the ear. We talked a little bit about how that originally came from with, I guess you said bells or TU or something like that?
It came from the TU, and they eventually morphed into the decibel.
Cool. Well, and how that works with this chart, which tells us, where we want the sound to be. I learned something because it has to be 20 dB higher. Even if it's really, really loud, it's still got to be higher.
Absolutely.
That can be really bad. Yep. But you want to target maybe 20 dB so I can hear in a conference room my sound that I want to hear and not the noise that I don't want to hear.
Exactly. So you can make this the audio of interest. You can actually reduce the noise floor a little bit with certain signal processing.
So I want to get the best equipment I can to get the sound separated from its noise.
Exactly.
Sounds very cool.
And the Vortex is the one thing that does that in a very small box, in a very inexpensive box too.
So I don't know about you, but I'm excited. Learning how sound goes through your ear, I kind of heard that, and maybe about microphones and stuff like that, but needing to have sound of certain level and knowing how to make the room and knowing how and what and who to hire to get it to work for you. I really appreciate you coming here today, Lance.
Thank you. Thank you for having me.